Okay, welcome back. So we were talking about functions, how to make our own, and now it's time for this wonderful thing called the stack. It's sometimes called the call stack or the runtime stack, but I will lovingly refer to it as just the stack. Okay? Usually, at least. So what it's going to do for us is answer these questions, like what in the world is C++ doing when I actually call a function? Like we've talked about, okay, it's going to go and replace whatever you called it with the x, and then it's going to execute the body and then come back to where you were, but what does that really mean? And how does it actually remember where it left off? Like, okay, it's going to call, main is going to call square, but then it needs to come back to main. How does it know what line it was on? Like, how does it know all this stuff? That's weird. Do I have a story for you? Okay, so the idea is every time you call a function, it gets pushed onto this thing called this stack. All right, so your program starts, and you can think of this like a stack of papers or something. You can only ever access the top one. So the very first thing, like the stack is initially empty, and then you run your program. The first function you call, the one that your terminal calls for you, is main. Right? So main is the first function, and it gets what's called pushed onto the stack. It's a weird metaphor. Don't worry. It'll all make sense in time. So main starts our program, and that is the bottom of our stack. Okay? And the stack itself is how functions know where to return to, because once you call a function, like square, for example, it remembers exactly what it was doing in main because it's right below it. That's where it stores this information. It knows where to come back to. Okay? And a very, very important thing is every function has its own memory for its local variables as well. So maybe I had, I don't know, I had x as my parameter for square, and that of course was a local variable for square. But then main has its own little local variables. Maybe it has like a and b and c. It could even have its own little x. They're separate x's. They're not the same. So that is the beauty of stacks. Okay? And every single time you call a function, like I don't know, maybe square needs to call sum for some weird reason, and sum takes a and b, which are a separate a and b to these ones down here. And the second sum is done, it gets taken away from the stack. Okay? Gets what's called popped off the stack. Okay? That's the opposite to being pushed. I know these are very weird metaphors. I don't really even understand them myself. So let's just roll with this. And that is the idea. Once sum is done, it goes right back to where square was calling it from. Okay? That is the idea. It knows where to return. It remembers what line we were on in square, which itself remembers what line we were on in main. Okay, so with that, let us talk about a very fun idea, which is globals. Globals and scope and the lifetimes of variables. Globals really is a word, I promise. Okay, so let's talk about this. And let's talk about it in terms of Harry Potter. Okay, I might need to change this example because maybe this is not your era anymore, but that's okay. Let's get started. So I'm going to say vim Harry Potter. That's CPP, but actually we're going to talk about book 4. That's Goblet of Fire, right? So let's talk about that one. At least I'm pretty sure it was book 4. Okay. The idea is you can have variables in many places, one of which is in a function, okay? So let's make a function called Goblet of Fire. And so this function, just like any other, it can have its own variables. Int blah, int Cedric. So I'm sorry to spoil this show to you, but Cedric dies in the movie. Okay, so this is what I'm trying to show you. Cedric is a local variable. Okay, it only lives for the life of its enclosing scope, we say. its scope is the goblet of fire function. Okay, that's how long it lives. It doesn't live after its scope is over. Okay, it doesn't live outside of its scope, which is quite sad. Okay, so that is Cedric. He only lives for a short period of time. I can see out Cedric all I want when I'm in the function. Okay, so that's Cedric, and that's a local variable. Variables defined inside functions are local. Okay? I can only see Cedric inside of Goblet of Fire. So for example, I'm going to call the function. And I get 42. I cannot do this down here because Cedric does not exist down here in main. It's like, what? Not declared in this scope. Hey. Okay. That's no fun. So that's a local variable. There are also global variables, and those are ones, we haven't really used those yet. They're defined outside of functions. Those are called global variables. Okay? So I'm going to make now Harry Potter. He's the boy who lived, so he lives forever. Yeah? So here's Harry up here. I don't know, 55 or something. And now Harry can be accessed and changed anywhere in this entire program. I can see out Harry down here, be like from main, and this one is from Goblet of Fire. I can also output Harry over here. Isn't that wonderful? I can output Harry wherever I want because he's a global variable. It can be accessed anywhere as well. So, if I recompile, of course, I can, from main, print Harry. He's 55, of course. I can change his value if I wanted to. I can print Cedric inside of Goblet of Fire, but I can also print Harry inside of Goblet of Fire too. He's a global variable. He can be accessed anywhere, and he lives for the life of the program. Okay, so that is Harry is a global, and Cedric is a local. And sadly, Cedric is going to die. All right, so this is how our program's working. This is how it's happening on the stack. So the idea is we have our main function. And main does not have any variables itself. Okay, I could define something in main if I really wanted to, but I have not. I would like to define Cedric, though, inside of Goblet of Fire. So I'm going to call Goblet of Fire, and that's when Cedric begins to exist. So I'm going to call Goblet of Fire right here. And then I have a Cedric variable that I can suddenly use. He lives right here, and his value is 42. I can print him out, of course. But then I also have Harry, who is a global variable. He lives in a different spot. The globals live outside of the stack. They live over here. Like, here's Harry. He's 55. That is the idea. And the problem is, once Goblet of Fire returns, once it's done with its work, we go right back to main, and Goblet of Fire stops existing. That's the point. So then we end up with this, and I'll copy this for effect. This is going to get erased. Okay? Goblet of Fire is going to go away, and Cedric is no longer. Okay? And we're back in main where we stopped. Okay? So we pick up on line 17, and let me print again from main after Goblet of Fire returns, because we're going to come right back to this line right after this function is finished. Okay, that's the idea. Are you ready? So, I think I saved it. So we're just going to print it one more time, is all. So Harry lives forever, Cedric unfortunately dies, stack frames, they go away after the function's return. Okay, Goblet of Fire is returning. We're going to go back to main, to line 18. That's where we need to come back to. Bam, we're done. No more Cedric, but Harry lives forever. So that is, in a nutshell, the call stack or the runtime stack. Okay, that's going to be very important to think about. All right. So now with that under our belt, it's going to make a lot more sense, this topic called references, which allow us to pass around variables or reference local variables from another function. Okay, so the idea is, I'm going to try and answer these questions for you. How do I modify the original values that I pass to a function? How do I do that? From that function, from that new function, that new place. And also, how can I possibly return multiple values at once? Because it's always return value, function name, and then you have your args. I can only return one thing, right? Well, this beautiful thing called references lets us return multiple values at once. It's going to be wonderful. All right, so a reference is this. It's what's called an alias for a variable. It's like a secret agent. It has multiple names. It does not take up any memory of its own. This is kind of a lie, but this is a good lie for right now. Okay, I promise. So a reference, all you have to do to make one is you use the ampersand modifier on a type itself. Okay, so you can say int ampersand, I don't know, z, is a reference to x or something like that. And this works any kind of way that you want it to work. So z is a reference to x. That is the point. And let me show you what this means. What this is doing is, apparently there is some x already. It has to exist. So x needs to be defined up here somewhere. Let's say x is 42. This is what it means to be a reference. So here's x over here. It's 42. When I say that z is a reference to x, this is all that's happening. I now have another name for the same place in memory. I could say z, I could say x, I still get 42. Okay? So that is the magic of this ampersand. And you might wonder, why in the world is this at all useful? I already had x, why do I need z to name the same thing? The answer is functions. Okay? First, I also want to show you that the space means absolutely nothing to references. Like C++ doesn't care if you put the ampersand right next to the type, in between the type and the variable, or next to the variable. C++ has no care in the world about white space. Okay? So it's just doing this. Okay? So for example, again, let's say that int x, or no, we're saying that y exists over here now. So int y equals something, like, I don't know, 55, bam, bam, bam. Somewhere later, we say, maybe across function calls, int ampersand x exists. This maybe could be a parameter. That's going to be the key here. And we're going to make that be a reference to y. So y is here, it's sitting here, and then x is just another name for that same box of memory. Okay? I could print it out, and I'd get the same thing. So let me show you this. So here is int y being 42, and then I'll say int x equals, int reference x equals y itself. So this is saying that x is a reference to y. Okay, are you ready? So what's going to happen now is we need to say, okay, reference to y, let's print you out. Let's make this bigger, actually. Let's print out y. That was the original variable. Let's print out x. Oops. They should both print 42. That is the hope. They're both 42, and I can change both of them. I could say y++, x++. These both affect y. These both affect the same place in memory. So what should y and x both print out to after I do these two lines? Drum roll, please. Oops. That's right, they're both 44 now, because I added 1 through y. So now I have 50. No, I guess I had 42. Sorry. Let's do some surgery on this example. I had 42. Then I had 43 because I said y++. And then when I did x++, well, it's the same place in memory. They're both 44 now. You see that? So x is just an alias to y. That's what a reference means. Okay? So now, this is beautiful, because this helps us pass original values around with functions. Okay? So let's talk about what happens on the stack when we pass something to a function. So let's pretend that we have an increment function. Let me make that for you right now. And the file that I'm going to write this in is called callbyreference.cpp for reasons that will soon become apparent. So here is an increment function. Int inc, and then it takes some x value, and then it adds 1 to x. And then here is my value v. It's 42. I'm going to call inc on it. And then I'm going to print out v itself. Yeah? Oh, sorry, this is void. It just adds 1 to x. It doesn't return anything. It just does something. And so, okay, v is 42. I'm going to increment v, call that function, and print out v again. What will it print? Oh, it's still 42. It's not 43. What in the world happened here? And the answer is the difference between this thing called call by value and this other thing called call by reference. So what's happening here is, here's the first one. I'm going to call this, for purposes, this is inc by value. What's happening here is how functions are getting called. Okay, so here's main. Here is v. And it's set to 42, and then we're going to call inc by value. Dun dun dun. And we call inc by value. And it gets an x. Okay? It gets an x. And that's eventually going to become the same value as the v. So this is what's happening when we call a function. When we pass a value to a function, pretend that there's some kind of like magical interfunction dreamland where the parameters get initialized to the arguments. So really, there's like a secret passage in between these two functions before inc by value begins. Essentially, this line of code that happens in between function calls takes place. It's like x equals v. That's what's happening. That initializes x to be the same as v, to be 42. You see that? It's like saying int x equals v. Because int x is the parameter. It's like doing int x equals v. As if it were, let's say, int x equals v. We know now that v and x don't exist in the same spot. We can't use them both at the same time, but in this interfunction dreamland, we can. Okay, so x is being populated with the value of v, and now we see the problem, because it's just a copy. These are two different memory locations, and sure, this x is 43, but we care about this v, and when we print out v, it has not changed. Okay, so this is what's called call by value, where you make copies. Okay, copies get made. You're not touching the original values anymore because you're making a copy of this parameter, of this value that you're passing along. Okay? This is in stark contrast to something called call by reference. Let's make an increment function that's by reference. Okay? And let me show you the difference. It's going to take a reference parameter, call it x. Watch this. And when we call this function, x gets initialized as if it were int reference x equals v. And I think you see what's going to happen now. This type makes all the difference. Because if we call this function, let's put these together like this, and then this, inc by reference now. Oops. Oh man, did it work? It's actually incrementing the value. Why? Well, here we go. Main holds v, which starts out being 42, of course. These technically are the same stack, but I'm drawing them separately for purposes. V is 42, and then we can call, again, because this is returned, like we're back to main, we're going to call inc by reference. I'll just say ref. And that's going to get something new, okay? This is x, but it's not a new integer. It is a reference to an integer. And so what I really should do is, how about everything that's green, everything that I color in green belongs to inc by ref, yeah? Let me do that. It has an x, but that x, it's int reference x equals v. So this parameter, this x, is not up here. It's not a separate box up here. It's this box down here, but it's called x now. That's the key difference. There is no copy getting made. It's just a new name for this v down here. Okay, that's the only way you can do this. Okay, we're going to make a new name for this v so that we can use it up here in this function. That's very, very useful, very, very handy. That does not work like this, okay? If you use a plain int, that value is getting copied. You cannot touch this value down here. But if you use references, then suddenly you have a new name for an existing variable that's not even part of your own function. That's beautiful. That's called call by reference, okay? So it becomes 43, and life is good. All right, so hopefully that was exciting. That was fun. I guess what I'd like to say to end this little subsection is that references, they save memory, okay? Because you're not copying things, they save memory, and that actually translates to time. Because imagine that you had a very large array that you were passing along or something, or maybe a vector. That would have to get copied to be a brand new, huge vector of a million things if you just used a reference instead. It was like a vector of int reference v. Then there's no copying at all, okay? No copying. And that saves a lot of time, okay? And also memory, of course. So use references when you can, and that is my lesson. Okay, so now we have another problem. So back, remember, to introduce functions, I'm like, oh, these main functions are getting long. Now, let's talk about multiple files, because I think you can agree that, man, these files are now getting long. Suddenly I have a bunch of functions defined, and then a main function, and I don't know what's going on. If only we could separate our programs into multiple files. It is possible. Let me show you how. Okay. So, the idea is, a lot of these things that it doesn't like the name of, we can separate our files into what's called .h files and .cpp files, like we have already, okay? .h files are called header files, okay? Called header files, and they end in .h or .hpp or .hxx. I'm going to use .h for this class. I think your book will too. Your implementation files, those are just the normal ones you already know, those have the same name, so it's like foo.h and foo.cpp, but also they end with .cpp. I like to use .cpp. Most people, I think, agree. Some people also like to use .cc, .C, .cxx. There are multiple different standard file names for C++. I like CPP, okay? And the idea is you're going to include your header file with single quotes, not like, let's go back to blue actually. You're going to include your header file with single quotes, and not those angle brackets. This is like it's a local file. This is like it's a special library file. Okay? These are reserved for system libraries. So we're not writing system libraries. We like what we have. And then you compile by giving multiple files at once. Let's see if I can get all these to go away. There they go. So that's the idea. You compile only the implementation files because including is going to copy things around. So let me show you this all working. I've made this example. Okay, so pretend we have these three files, main.cpp, foo.cpp, and foo.h. So main.cpp holds the main function. That's where our program starts, and it's going to call bar of foo of 42, okay, and then return 0. Well, how does main.cpp know about these functions? Well, it knows about their declarations, which exist in the foo.h file. That's where you put declarations of things, okay? Declarations of functions go here. And then, in the corresponding foo.cpp, you customarily include your header file, and then you go implement those same functions. Functions in the header, in the .h file, are implemented here. So the functions, I guess, defined in the .h file are implemented in the .cpp file. And that's the strategy that you play. You can have as many .h and .cpp files as you would like, and they split up your program very, very nicely. Okay, so that is the idea, and let us talk about this. The very last thing, maybe on this slide, is this hashtag include just means copy and paste foo.h right here, please. So that copies and pastes a file. And that is why you only have to compile the implementation files, because everything else is getting copy and pasted anyway, because you're including those headers. Okay, so that's a lot of words, a lot of new things. I'm going to show you exactly how to do it. Let's convert our sum of squares functionality into a library. So let's see here. I don't have it here, but let's go up a directory. Let's go out to lecture 11 and back to sumsquares.cpp. So I'm going to copy all of this. Okay, and then we're going to go back to lecture 12, and we're going to go, well, I guess we can go anywhere. I'm going to make a new file. You know what? I'm going to make a new folder. Mictor, we'll call it Sum of Squares Library. Okay, now I have a folder. Let's cd into that. And that's where we're going to work. Okay? Let us make some files now. Let's make main.cpp. Oh darn. That one thing that I wanted to copy, it didn't remember it. And actually, have I? Oh, there it goes. Cool. It did remember. Awesome. So here's what I would like to do. We're going to have main.cpp. That holds the main function. And then we're going to have sum of squares.h. and sum of squares.cpp. So these are going to hold declarations of, let's see, of sum, square, and sum squares from 1 to 2. And these will hold the implementations of those functions. Of all those from over there. Okay, so these go hand in hand, the .h file and the .cpp file. So let me show you how this is working. Okay, are you ready? So this is just main.cpp. I would like to get rid of most of this stuff. So I'm going to make a file called sum of squares.cpp. Let's do that one first. And we're going to copy, well, we're actually going to cut and paste all of these things. We're going to define all of our functions here in the .cpp file. So there's that. And customarily, we include the header file as well. It just makes things go nicely. Okay, back to the main.cpp. We also get rid of these declarations. Those go in the header file. Okay, so I'm going to make a file called sumofsquares.h, and oops, and then we're going to paste this all here. Okay, so let me write a ton of comments now. .h files. So this is .h down here. .h files are header files. And this is a comment. They hold declarations of functions. It's like we're making our own library, okay? We're making the sum of squares library for ourselves right now. Okay, so that's the .h file. And then we have .cpp files. Hold implementations of our library. So again, this is the sum of squares library. Everything that was declared in the .h file. Needs to be implemented in the .cpp file with the same name. Okay, so this is sum of squares.cpp down here, I hope you see, and then sum of squares.h, oops, holds the declaration of all those functions that we're implementing in sum of squares.cpp. Okay, I hope you see that. And then main.cpp wants to use that one thing, so we're going to include, with double quotes now, sum of squares.h, and that gives it access to, because this is going to copy and paste the header file right here. And that's how it's going to work. Okay? So these are all talking to each other. This is pulling from sum of squares.h. This is pulling from sum of squares.h. This is implementing everything over here. Okay? That's how it's working. Okay, so let me show you this all together, and we're going to compile with G++, and then every .cpp file. Those are the implementation files only. Okay, are you ready? So, I'm going to say G++, standard equals C++17, then both implementation files, main.cpp and sum of squares.cpp. We need both of these because the implementations are split across both of these files. Okay? The main function's here, and then all the other functions live here. Are you ready? Oh, oops. I need to make it something other than a.out, and we'll call it, I don't know, we can call it main. So now, I have made a main executable program that is the compilation of both of these files all together. And I can run them, and we get no difference, but we've split up everything. Like everything that belongs to sum of squares functionality is declared here and defined here. Okay? So I know that's a big deal, but you're going to get a ton of practice with this. All right, and let's move on now to this wonderful idea that unfortunately needs to exist. Okay, so because include, number sign include, blah.h, it's going to copy and paste. Okay, this just copies and pastes this file into whatever file you're using this include thing with. Okay, that's always going to be the case. It's impossible, or sorry, it is possible to infinitely include the file. Okay, which is very unfortunate. Let me show it to you. So let's go quit out of this. Let's go back out to the normal lecture 12 folder, and I'm going to make an infinite inclusion .h file, I guess. Why not? Vim infinite inclusion .h, and I'm very sorry about this, but it's going to happen. Okay? Or you know what? I think let's just stick in our sum of squares library. I'd rather stay there. I'm going to make sum of squares.h horrible. Okay? Watch me do this. I'm including the file within itself. Are you ready? This is going to go horribly wrong. Dun dun dun. Oh. Let me show you this, because this is fun to look at. Here it is again. Whee! Here it is. Oh. Keeps going actually. Whee! All the way up to here. It's like, oh, okay. You're including this file within this file, within this file, within this file, and it gives up after some time. It does try, but it gives up after a while. It's like include nested way too deeply. Don't do this. So it's going to copy and paste this file within itself. That's really unfortunate. And you normally don't ever do this. You don't include the file within itself. But it's possible to include file A, which, like, file A includes file B, and file B also includes file A, and that's another way to have this infinite inclusion happen. Okay? It's a lot more subtle in practice. You're never usually including yourself in yourself. It's just indirectly. Okay? I promise that this is a problem, and it can happen. So I want to show you how to solve it once and for all. Okay? We can stop this. We can stop this from being a problem with this thing called header file guards. And guard is like it guards against what's happening. Okay? So, this is what you do. This is a special compile time variable that we're about to create that keeps track of whether or not this header file has been included already by ourselves. And so this is the secret. You say if ndef, and then you give some variable name. It's usually the name of the file, all capitals, but with the dot replaced by an underscore. Then you say define that thing. Then you give the entire original contents of the file. This is the original file. And then you say ndif. This is a compiler level if statement. It's as your program is getting compiled, it's making a little if statement for itself. It's like if this variable has not yet been defined, define it, then run all this, then we're done with our if statement. It's like the closing brace. And the beauty of that is only will it not be defined if we haven't already included all this, because that's where it gets defined. Okay? It's a bit of a trick, but it's wonderful, and it's going to make sure that this header file has not yet been included. And if it already has been, this is going to be false. It has been defined, so it's going to just jump right out here, and it's not going to keep on infinitely including itself. So that's the secret. So I can say, I can actually keep this problem in it and do this. If ndef sum of squares h, then I can say define sum of squares h, and then down here I can say ndif. And now suddenly it's happy. This is not a problem anymore. It works. This is not a problem at all, because once it does this, it's going to copy and paste all this again, but it's like, oh, yeah, it already has been defined, sum of squares, so I'm just going to skip over this copy, okay? That's the point. That's the beauty. So if that made no sense at all, I'd be happy to talk about it in office hours. This is a weird concept, I know. This is one of those few things that it does better to memorize and then ask questions later. This is a wonderful, wonderful 3 lines, okay? It's called a header file guard. Okay, and that is going to help you avoid infinite inclusion inside of loops. All right, so my last example for this set of slides, or for this week at least, is to talk about counters, okay? So remember that silly counter example I made at the start of the class? We're getting very close to being able to do that ourselves. So we're going to make a counter for functions. Okay, using functions, we're going to make a little library for ourselves that can be that models a counter that can be incremented and decremented, etc., etc. Okay, and this is going to help functions make sense. I promise they will eventually make sense. It's just going to take a lot of practice. Okay, so let's design what we want our functions to be, because we want our counter to like exist, and it's going to keep track of some kind of count, and it'll start at 0 maybe, and every time we increment it, it'll go 1, 2, 3, and we want to eventually get back the final count, maybe reset it back to 0, etc., etc. So let's talk about all the things we might want to do. So we're going to need a count variable, definitely, to keep track of our counter's count. We'll put that in the CPP file so that only we can see it. Okay? And we would like to initialize our counter to be 0. We'll do that with a function. Okay? It'll only ever get called once, and that'll make sure that our count starts out at 0. Okay? So that's count. And then we'll have an increment function, which takes this count variable and adds 1 to it. Maybe we want an extra fancy counter, like this one can only go up, but ours can maybe go down, so we'll make a decrement function. So like if this were 2, if we decremented it, it'll go back to 1. Not bad. Maybe we can also have a reset function that'll reset count to 0. So if this were 2 again, it'll go right back to 0 after we increment and then reset. Though technically we could initialize it again, but we like to only use the initialization once. And then we'll also need a get count function, and that'll give back our current count, so that we can give that back to whoever is asking about it. Okay? So that's kind of the plan, and let's talk about all the functions we're going to need now. And of course, PowerPoint doesn't like the name of any of this, but that's okay. So, there we go. Here are our 5 functions that will be defined inside of counter.h. We're going to initialize our counter, increment it, decrement it, reset it, and get the count back. Okay, so let's implement this. Let's make it happen. This is our own little library. I'll make a new folder for it. Counter. I'll make sure I'm in it over here too. There we go. Are you ready? So it's an empty folder right now, but let's make counter.h so that we have all these things to do. So we want our header file guards as usual, so let's include those. If, ndef, define, and then ndif. And then here are all our functions that we would like to have. We want all of these things. We want to be able to initialize the counter, increment it, decrement it, reset it. Oops. And then get the count. What are the types of all these? Well, initialize counter should be void. Increment should be void. It's just going to act on this global count variable that doesn't exist here. It's going to exist in the .cpp file. Decrement, void, it just does something. It decrements the count. Reset, also void. It's just going to set the count again. Get count, though, finally, is going to give back an integer. That is our current count. Okay? So this is how we would like to use it with these 5 functions. So now maybe let's make a main.cpp so that I can show you how we're going to run this. We're going to include counter.h, and then here's what we can do. We can be like counter, init counter, sorry. We can say init counter, so the count should start at 0. We can even print it out. Oops. Get count. So we should see 0 here. And then we can increment it. Inc. And we can do that a few times. So now the count should be 3, right? Hopefully. And then we can decrement it. So it should be 2, right? Oops. So this should now be 2. Hopefully. And then we want to, what else can we do? We can say reset to make it 0 again. that should make our counter 0 now when we get count again. And yeah, we can increment it as much as we want and keep on going, and then maybe at the very end it's 1. Yeah? So these are all the things that we can do if we had all these library functions defined in counter.h. If we had all of this, and they kept track of some secret counter somewhere, we could use them like this and get a lot of use out of that. Yeah? So that is our counter library. Let's now go and implement it. So we can say, we can just copy all this and then go to counter.cpp. So I want to include counter.h, and then, darn, all of these. There we go. And now we're going to go and implement them. So that needs to do something. There we go. That needs to do something. So does that, so does that, and so does that. Okay. Let's make it all nice and pretty. What do we need? We need a count variable. It needs to be global so that we can see it, and nobody else can, though, because it's only going to be global to our file, counter.cpp. So here's count. Keeps track of the count inside the counter, and I shouldn't have saved the file, darn, because it made it all pretty and it made everything go away. Init counter is going to set the count to be 0. So that's what init counter should do. Inc should increment the counter to be 1 more than it is, which means increment the count itself, count plus plus. Decrement should be count minus minus. You see how this is also useful when you have a global variable and you're just doing things to it? Reset should be count equals 0 again. And the idea is you're going to call init just once at the very beginning of the program, and then reset does the same thing later. Just for us as programmers, they're different. And then get count is going to return back the count. And this is the only way, because this variable only exists for us in this file. That's the only way we can see this in main.cpp. Okay, so again, here are our 3 files. Main.cpp, that's using these functions. It's including the library header so that it knows what's going on. Like, you can do these things, but I'm not going to tell you how we do them. And then counter.cpp is where we go and define how these functions are actually working and the data on which they are operating. Okay, so that should be all. We'll init our counter, so count is 0. We'll increment our counter, so count is 1 more than it was. We'll get our count, which always returns back the current value of count. This is all going to work. This should all print out what we think it should. Okay? So let's go and compile this. If we can go back to that. It's main.cpp as well as counter.cpp. You don't include the .h files because they've already been copied and pasted through the number sign include. And, oops, I don't want it to be called a.out. I want it to be called, I don't know, counter or something. And so now I have that. I've compiled these 2 files together to make a final executable program called counter that I can go and run, and bam, it should print everything we wanted. So counter starts at 0, so this should print 0 as it does. 0, 3, 2, 0, 1. It follows all of our guidelines, okay? And it's working. It's beautiful. I hope that this is fun. I encourage you to study this program. This is a very important one to know how to do, okay? This is a great one to study. So that is everything that I wanted to talk about today. Okay, we have come very far. We have learned how to make libraries that exist across multiple files. We make sure that they're not going to infinitely include themselves. But we've split up our programs logically now into files that deal with the same thing, like counter stuff, and then the main function stuff. And we are just separating all of our concerns. And it's a beautiful thing. okay? And the implementation, the meat, is all hidden away over here so that the user who just wants to use the counter library, all they need to do is look at this file to see how to use that, okay? They don't have to care what's in counter.cpp, how it's really being implemented. They just need to know all the types involved and the order in which they can use all of these functions. Okay, so this hopefully was very fun for you. I enjoyed it. It was a cute little example of counters, and that is where I want to end today. So go study for the midterm. Good luck, and I will see you in a lab video, but that lab is going to be due very long from now because of the midterm and all that. But I want you to at least see it so that you can potentially get started early if you would like. Okay, so we're going to come back and talk about const parameters, and that will be the end of these slides. But that will be next week. So I will see you then.